people have tried technique because for the spectral lines, we have the velocity information. And we know that along the different spiral arms, the gas moves at slightly different velocities. So if we plot the position of these clouds in the galaxy, for example, at the galactic longitude, versus their corresponding velocity information, you get structures like these. And in these structures, you see some enhancements in brightness, which is typically believed to be due to spiral arms. So they model this as some spiral structures, and this is how we try to understand the larger scale structure of the Milky Way. So then another thing people typically use is to understand the distance information from star forming regions and molecular clouds. So if you have already some star clusters or H2 regions formed within these regions, we can use the parallax information, and using the parallax, we can reproduce the face-on view of the galaxy with all these different estimates of different regions overplotted. And such plots show that there are some enhancements in certain regions, which is believed to be corresponding to the densest regions of the spiral arms. So then if we try to overplot the models which we obtained from the longitude velocity diagrams with the corresponding distance estimates of the star forming regions, they match quite well. And this is how we try to infer the morphology of the Milky Way. So shown here is the most scientifically accurate picture of the Milky Way produced so far. Of course, this is an artistic impression, and this is by Reed and Seng 2020. So from our current view is that Milky Way is a barred spiral galaxy. So we have the supermassive black hole Sagittarius A located at the galactic center, but then it also has an elongated bar. And Milky Way is also believed to have 4 major arms, then some minor arms like the local arm. Then we have some spur-like structures, which are kind of branches, which is emanating from the major spiral arms. So if we look at this, this picture, the latest about our galaxy with some of the external galaxies, what we can immediately see is, okay, in this picture, we have information about the densest spiral arms. But if we look at the true pictures of external galaxies, there are a lot of the small scale structures within the spiral arms or the interam regions, and it's not as a tightly woven spiral like the image here. So we are missing the intricate features at kiloparsec scales. So there has been tremendous progress in understanding the slightly smaller scale structures at hundreds of parsec scales. For example, in the last decade, there is a interesting discovery about filamentary structures seen in the infrared maps. So shown here are the 2 maps in the inner galaxy in the first and fourth quadrant, the infrared emission maps at 8 micrometer. And in these both maps, you can see some structure, a highly linear filament-like structure in these images, which are extending to hundreds of parsecs. And when we are looking at these dark features, they are probing really dense and cold gas. Why is it the case? Because we have this bright galactic background from the warm dust in the region, but here we are seeing more or less some kind of extinction structure, and it is blocking all this background light from behind, which means that this is highly dense even in the infrared. So these kind of clouds are called infrared dark clouds, and they appear in many morphologies. But specifically, people are interested in trying to understand this kind of filamentary clouds, which are extremely linear, string-like, and it's very extremely long compared to the typical clouds we see in the galaxy so far. So people try to understand where they lie and how these properties are. they came up with the two major kind of categories of these giant molecular filaments. And first one is termed of bonds. So bonds are filaments with a very high aspect ratio. So their length is to width cross like exceeds around 50. And another thing is, if you look at the spectral line data, their velocities matches closely with the nearest spiral lengths. So delta V is less than plus or minus 10 kilometer per second. And another thing they observed is these kind of giant molecular filaments, they lie within 20 parsec of the galactic midplane. So they are more or less aligned very close to the midplane. So studies suggested that these kind of bonds may be tracing the spine of our galaxy, and studying the bonds, we could actually map the molecular skeleton of Milky Way. Then there is another class of filaments identified mainly in the external galaxies. If we look at, for example, the H-alpha image from the Hubble towards the M51 region, what you can see is these kind of narrow structures which are lying between the two spiral lamps, and sometimes they are kind of emanating from the spiral lamps, but the orientation is completely different to that of bonds, because bonds were mostly along the spiral lamp, whereas these kind of structures were perpendicular to them. And such structures were also observed in the magnetohydrodynamic simulations. For example, shown here is the simulation from Kim and Ostriker 2002, and you can see the formation of these structures. And though there are multiple scenarios proposed to explain them, so the most popular belief is that these are produced by the passage of molecular clouds through the spiral potential. And when they pass from one arm to another, it experiences a shear force, and this will stretch the clouds in such a way that they form structures like this. And such structures are called spurs or feathers compared to the bonds. So these feathers, they are narrowed as lanes perpendicular to spiral lamps, and such feathers are observed in hundreds of external galaxies, and they extend from several hundreds to kiloparsec scales. So they look like a fanned out feather, like that of a bird. So they came up with this interesting name. And then the studies tried to see all this already identified giant molecular filaments, either from the infrared or from the spectral line molecular data in the millimeter. And they tried to overplot their velocity and position information with that of the spiral lamp models. So these are two such studies showing the distribution of all the identified giant molecular filaments with respect to the models of our spiral lamp. And we can see that a few of these filaments, the kind of velocity is closely associated with the spiral lamp, but they fall quite nicely within the spiral lamp region. So they are more of consistent with the bond-like scenario. Whereas there are certain filaments which are far away from any of the spiral lamps, and it locates in between. So they are more potential spurs or feather candidates. But these were all clouds of size 100 parsec or so. So in this one, one important point we should note that all the identified spurs or bonds, whatever giant molecular filaments, they were mostly identified in the Scutum Centaurus and Sagittarius Carina. And if you look at the Norma arm, which is shown in cyan here, for example, you are not seeing any filaments there. So why is it so? Because if we look from the solar system towards the galactic center region, the Scutum and Sagittarius, these two arms are relatively closer to us, whereas the Norma arm is more far away from us. So in order to identify the filaments in the Norma arm, definitely we cannot go for infrared emission, because there will be strong contamination from the foreground, which will mask all these infrared extinction features. And if we look at the submillimeter data, molecular line data, we need sensitive surveys to probe the weak emission from these faraway clouds. So with this idea in mind, we have searched for possible bonds or feathers in the SEDIGISM CO survey. So it's a recent survey taken using the APEX 12-meter telescope in Chile. So it probes the molecular lines at 1 millimeter and covers 78 degrees square of the inner galaxy. So this in this image shown in gray is the coverage of the SEDIGISM survey. And if you look at the spiral lamps, you can see the red one is the norma. So in the fourth quadrant, you can probe all the emission corresponding to this inner regions close to the galactic center. And the 13CO221 being a relatively higher density tracer than the 12CO120, which is the typical one, we can trace the cold and dense interstellar medium. So first what we did is we had almost 78 tiles, CO tiles, each of having size 1 degree. And we tried to combine all the data in this SEDIGISM survey to create a large mosaic of the entire galactic this coverage. And shown here is the integrated intensity map of the entire SEDIGISM field in the whole velocity range. So we integrated within minus 200 to 200. And you can definitely see these emission features and even a few pixels in this map corresponds to molecular clouds of scale a few parsecs. So if we look at the entire integrated emission, you cannot perceive any filamentary structure as such because this is a combination of several features from several spiral lamps. So to identify possible giant filaments, we have integrated the emission within 10-kilometer intervals so that if there is some velocity coherent emission, we can immediately identify them. And created several bins like this. Shown here is only the few of these 10-kilometer second moment maps in the first quadrant of the galaxy as an example. And we have visually inspected these maps to identify filamentary structures. So here I want to bring your attention to the fact that there are several filament finding algorithms present nowadays so that you can use these automated algorithms to identify filaments. But why we went for visual inspection is that the type of filaments we are looking at exceed a size of hundreds of parsecs. So in these filaments, definitely there will be star formation activity because we are looking at dense molecular clouds. And due to the star formation activity, the filament will be broken into small pieces. So if we go for the automated methods, we won't be able to identify this as a single structure. So such kind of scenarios, we really need visual inspection to identify the filamentary structure. So while looking at this maps in the fourth quadrant, we have noticed a narrow wavy feature in the longitude range 326 to 356 degree in the velocity range minus 95 to minus 75. So in the 2 velocity bins, each of 10 kilometers per second, we have observed this kind of a structure. And if we look at the length is to width, so it is having an angular extension of 30 degree, whereas the width corresponds to 0.5 degree if you take an average width. So it implies that an aspect ratio of 60:1, which means it's a highly filamentary structure. And shown here are 3 example individual velocity maps. So these are maps of resolution 30 arc second. And here also we can see this kind of wave-like feature. And this latitude range minus 0.5 to 0.5, but you can see they are confined to specific latitude range in the specific location. And if we compare this with some of the channel maps in the other velocity ranges, for example, first one shown here is the channel map at minus 85 corresponding to the wave, whereas the bottom panel shows a velocity map at minus 40. This corresponds to emission from the scutum arm. So if we compare the wavy feature emission with the scutum arm emission, you can clearly see that at minus 40, the emission is more patchy and diffuse, and it doesn't have any specific latitude range. It extends from say minus 0.5 to 0.5. Definitely you see some kind of substructures within the diffuse emission, but If we compare the wavy emission, it is more confined and filamentary. But we also see some breaks along the wave, as I mentioned. This is due to star formation activity. So if we look also at the 12CO120 data from the 3 millimeter MOPRA survey, we can again see the emission here. So this is slightly stretched image for a better visualization. But in the 12CO, you see more a broader wavy feature, but the wave structure is apparent, but it's slightly broader because 12CO120 is less dense compared to the 13CO emission. So we will see some of the relatively diffuse components. And then we tried to estimate the distance using kinematic calculations. And we found that towards the lower longitude range at the 330 degree, the distance is roughly 4.5 kiloparsec. Whereas if we move more towards the galactic center, towards the proximity of the galactic center, we see that the distance is approximately 6.5 kiloparsec. So it has a distance range between 4.5 to 6.5. And if we assume a distance of 4.5, the lower limit distance, we find a lower limit length as a 2.4 kiloparsec. So this is the largest of such a structure in the molecular emission observed. And using the CO data, we tried to estimate the column density and resultant mass, and we found that the structure is at least a 9 million solar mass. Now let us look at the position of this structure to see whether we can infer something about the property of this structure. So if we look at the H1 emission, definitely H1 traces more of the lower density gas. So we are seeing basically the outer diffuse envelope. So in the H1, we were not able to identify the wave structure in the moment map, but we could see definitely bright emission corresponding to this feature. And if we plot it in the longitude velocity map with respect to the spiral arm models of Reed et al. 2019, this red curve shows the model of the norma arm, whereas this yellow shows the 3 kiloparsec arm. Both are shown in the face-on view here as well. So we see that the emission actually up to half of or 1/3 of the longitude range, the emission is consistent with the norma arm, but then it slightly move out of the norma arm and branch out. And at this longitude range between say minus 350 to 340 degree or so, you can clearly see that there exist two components for the norma arm.
Veena,
so one major,
yeah,
sure. Yeah, one major part and this branched part. So we see that it's more perpendicular to the spiral arms. And one problem when we really estimate the distance at these regions is that there could be non-circular motions due to the galactic bar. So we also try to correct for this using the simulations of Sormani et al. 2018. And here we find that even after correcting for the non-circular motion at the galactic center, still we get a distance of 4.5 to 6.5, which means that this is really an interam feature. And even in this interam part itself, the length of the wave is almost 800 parsec. And the typical width expected for the spiral arms is just 0.2 to 0.3 kiloparsec, which means that this is definitely cannot be confined to one spiral arm. So if we look at this relative orientation of this one with the external galaxies, we see that it's more consistent with the feather-like features seen in the external galaxies. But this one, apart from its unique orientation, it also has this interesting wavy structure. So considering its uniqueness, we named it as Gangotri wave after the Gangotri glacier, which is the origin of Ganga river, because Milky Way is also known as Agash Ganga in many Indian languages. So this has been published in Astrophysical Journal Letters in 2021. So is Gangotri wave the only structure, such structure identified in the galaxy? No. In fact, people have seen wavy structure in the distribution of open clusters in the Sagittarius arm in 1992 by Alfaro. Then there were reports of a recently discovered Radcliffe wave, which is in the solar neighborhood. They observed a oscillatory structure in the molecular clouds. So the origin of these wavy filaments or wavy structures are not clear. People thought that maybe this could be due to the passage of dwarf galaxies through the galactic midplane, which can cause ripple-like perturbations, or there could be also bar and spiral lamp interaction. So the Gangotri wave is standing out because people have observed these in the star-forming clusters and clouds, but not directly in the molecular emission. So we, for the first time, are seeing such a wavy emission directly in the molecular maps. So are there more kiloparsec inter-ramp clouds? So if we look at the distribution of high mass cores in the galaxy, we see some density enhancements in the inter-ramp region. So this one corresponds to the Gangotri wave, and this enhancement is already an identified spur, which is known as the Aquila spur. But apart from that, we also see an enhancement between the scutum and norma arm. And if we look at the longitude velocity maps, here also we clearly see this structure like a bridge connecting the arms. And if you look at the distribution of Atlas Gal millimeter clumps, we can see an enhancement again here. And if we overplot that with the moment map, the distribution of all the sources, we see a structure here. But we don't know the true structure, whether this is wavy, filamentary, etc. Because in this case, if we look at the solar system from here towards this region, we are actually looking along the line of sight. So it's very difficult to perceive the true structure. And recently, there has been several reports of such kind of structures which are perpendicular to the spiral lamps. For example, Kuhn et al. Identified 1 kiloparsec linear structure with a 7:1 aspect ratio. So this is, they did with the Gaia data. And they concluded this could be either a sub-branch of Sagittarius arm or an isolated structure. And Colombo et al. 2021, they have studied some of the giant filaments in the outer galaxy, because most of the studies focus the inner galaxy region. And they seen several inter-ramp giant filaments, so which were, as I said, they were in the inter-ramp. So all these recent studies show that Milky Way could be more irregular than a tightly woven grand design spiral. So to summarize, these giant molecular filaments redefined our large scale spiral lamp structures. And we have identified a kiloparsec scale molecular wave in the inner galaxy, which we named as the Gangotri wave. And its orientation is more consistent with it being a feather or spur-like structure than a bond candidate. And with the recent high sensitive and high resolution surveys using different techniques, we are able to identify new inter-ramp bridge or structures which can redefine our current view. And it may point that Milky Way is more flocculent than originally thought. So with this, I will stop here and thank you.
Thank you. Thank you, Veena. Very nice work. Congratulations for this. So now questions from, let's say, first offline participants. Is there any volunteer? Yeah, I don't. Yeah. Is there any question from offline participant? You are muted. You are muted, please. Can you unmute it?
Yeah. Can you hear me?
Yes. Yes.
Yeah. Yeah. That was a really very interesting talk, and I was fascinated by this large feature that you have seen, 2.4 kiloparsec long. I was wondering whether you can say anything about the age of this feature, because it's in the inner region. Differential rotation won't affect it, right? Otherwise, you could have placed some limit.
Yes, but we expect it to be at least few millions of light year, which is the typical age of the giant molecular clouds. But And we also see towards the dense regions, there is already star formation activity happening, few H2 regions, and also the lower limit is few million years, but we don't really know.
Okay. And the ones you showed in the outer parts from Colombo et al., they would suffer differential rotation, right? So
yes. Yes,
so
but
they
they haven't done this with a detailed study, because unlike the structure here, they are much smaller scales of the order of a few tens of parsecs.
Oh, okay.
Yeah.
Okay. Thanks a lot.
Now, second question is from Balchan Joshi. Please unmute yourself. Can you make him unmute, please? The host, can you unmute Professor Balchan?
Yeah. Okay. Yes. Finally, I got unmuted.
Great.
Yeah. Thanks. Veena, a very, very interesting talk to see these really fantastic microstructure within the interarm region of the galaxy. My question was a more practical one. So with all these new details which you sort of presented from different studies in the recent past, is there a tool by which one could actually identify individual filaments in a given line of sight? So is there a practical tool which would allow you to sort of identify what all filamentary structure you cross in a line of sight? Okay,
so first of all, for the interim clouds, most likely there is less star formation activity unless they are dense enough. So such structures, I don't know, like we cannot use, for example, parallax from the stars or anything. And we cannot also use Gaia, for example, because there are no stars within these clouds. If they are dense enough in at least in certain localized regions, and if there are mesas, for example, then we can use this parallax measurements of mesas to accurately pinpoint the distance, or to say that whether they really are in the interim or not. The most challenging part for a structure is, in case of this wavy feature, it's much easier because as I mentioned earlier, its width is or its length is much larger than the typical width of a spiral lamp. So we can see structure extending more. But if we see a structure much lesser size scale, for example, only few hundred parsec, and if we find it to be closer to the spiral arm, we really don't know whether it's belong to the spiral arm or slightly outside, because there are several models for the spiral arms. And you cannot actually accurately pinpoint the exact location unless it is extremely large. So if we compare in the external galaxies, people can identify even smaller structures which are perpendicular, but in case of Milky Way, this is practically still difficult.
Okay, thank you. Any participant from offline? I can take one question. Okay, I don't think that there is any questions from the offline person. So thank you, Veena, once again. So we shall move now the next talk. Next talk is by Akanksha Khandelwal from PRL.
Yeah, so now it's working. So yeah, there is a question from the offline participant.
Yeah.
Hello?
Yeah.
So there is a question from the offline participant.
Okay, then one question and I can take up, otherwise the time doesn't permit me. Yeah, please, one question.
So we've been trying to unmute actually, but I think there are some issues.
Yeah, okay.
So
Please go ahead.
Veena, very nice talk. I have just one question. I had two, but I'll ask you just one in the interest of time. Are you trying to look for the fact that there could be more star formation that could occur here in the form of cores and so on, that it may not have already formed, but is there possibility of probably some form of star formation occurring because you have these kind of shear waves and so on? Some cores or something, may not be high mass, maybe low mass. Yeah.
This wavy feature, we definitely see several even H2 regions and bubbles, because once we look in, we are able to identify this in the SEDIGISM survey, means that it's already, because SEDIGISM 13CO, the detection limit, 3 sigma detection limit is 3 into 10 power 21 per centimeter square for the NH2, H2 column density. So once we see this in the 13CO, definitely means that it has a column density value above 3 into 10 power 21.
To characterize this versus what you have in the spiral arm.
Yes, exactly.
So there are a few questions in chat. Can you please answer them? That you just look at into chat and answer it.
Yeah. So it says like the dense gas fraction.
Yeah,
so,
I would say just I'd go ahead with this, but you just answer that by tapping. That will be very grateful to you. Okay, thank you very much. So the next talk is from the Akanksha Khandelwal from PRL. So we'll be talking on discovery of an inflated hot Jupiter TOI-1789b around a late F-type star. Now, Akanksha, please.
आपने को होस्ट नहीं बनवाया इस रूम को, ये रूम को होस्ट होना चाहिए। जावेद सर को बोलो। जावेद को कॉल करते हैं।
इनको को होस्ट ड्राइव देना है
LHC 104 को
LHC 104
सर LHC 104
Yeah, please look into these things and make a host so that we cannot waste the time. Yeah, good. So Akanksha, you please start. I'll ping 3 minutes before the discussion time. Javed, can you unmute yourself? Mute, sorry. Mute, please. Javed, you mute yourself, please. Yeah, please go ahead.
Hello everyone, I am Akanksha Khandelwal, PhD student from Physical Research Laboratory, Ahmedabad. So, recently we have detected an inflated hot Jupiter TOI-1789b around a late F-type star. So this work has been highlighted in various news, and it also has been a ISRO story of the week. So in this talk, I will discuss our work related to this detection. So first of all, I would like to thank all my collaborators for their significant contribution to this work. So now I will discuss what are exoplanets. So exoplanets are extrasolar planets or planets beyond our solar system. Their true masses are below the limiting mass for the thermonuclear fusion for the deuterium, and they can be, depending upon their masses and sizes, they can be characterized into gas giant, Neptunian, super Earth, and terrestrial. So in this figure, you can see the number of detected exoplanet with respect to their discovery year. And here in this figure, you also can see the most of the planet are detected by transit and radial velocity method. So now I will discuss what are these transit or radial velocity methods. So when a planet passes in front of the star, then it obscures some of the light. So we see dip in the brightness of the star, as you can see in this animation. So the radius of this planet can be determined by the fractional change in the flux of the star. So for any astrophysical body, the mass is one of the most important parameter to determine. So for exoplanet detection, we use high precision spectroscopy to determine the mass. So for that, we calculate the radial velocity. So for the radial velocity detection, we use the Doppler spectroscopy. So when a planet and star are gravitationally bound, then they orbit around a common center of mass, as you can see in this animation. So when someone is observing far away from that star, then he or she would see the shift in the spectra. When the star is moving towards the observer, then he will see the blue shift in the spectra, and when star is moving away from the observer, then he will see the red shift in the spectra. So by measuring the shift in the spectra, one can calculate the radial velocity. So for if any exoplanet or any other body are present in the gravitational field of that star, then it will show these kind of sinusoidal modulation. So since it is periodically, the star is periodically wobbling around this common center of mass, then we see the periodic variation in the stellar radial velocity. So now I am coming to the main target of interest of mine. So TOI-1789. So it is initially identified by TESS, which as an probable exoplanet host star. It has a visual magnitude of 9.7, and these are the information that are available on ExoFob TESS page. So this is this figure shows the normalized light curve of the TESS, and these red triangle shows the position of the transit. So, means that TESS has detected it as detected 7 transit in its observing period. Now it has a visual binary candidate at 1.3 arcminute separation, and TESS has observed it in long cadence mode, which is 30 minutes, and the error in the radius of the planetary candidate by the TESS is 27%, which is reduced by our observation from Mount Abu Observatory up to 9 to 16%. So we did ground-based photometry with PRL's 43 centimeter telescope. This is the 43 centimeter telescope, and this is the light curve on the upper panel, which we collected the data from this 43 centimeter telescope, and for that we used 2 CCDs. One is the TRIAS and another is the Endor, and these blue points shows the TRIAS data point, and here these green points shows the Endor data points. So we did take these observations in high cadence. So now for determining the mass and spectroscopic parameters, we used PARAS and TCS spectrograph. With the PARAS, we take 16 spectra, and with the TCS, we take 21 spectra. So PARAS is attached to a 1.2 meter telescope. It is a high resolution spectrograph with resolving power of 67,000, and TCS is attached to a 2 meter telescope at Tottenberg, Germany. So independent of the transit or a photometric method, we also tried to check the orbital period with our RV observation. So for that, we did the generalized Lomb-Scargal periodogram on the RV data sets, and we found the most significant period is at 3.21 days. So here on the upper panel, you can see the generalized Lomb-Scargal periodogram, where these green line represent the 3.21 day signal data, and there are also 2 other significant peak. One is at 1.45 and another is 0.76 days. So when we remove these 3.21 day signal into data, these 2 peaks also removed, which shows that these 2 peaks are alias of this 3.21 day signal. As you can see in the residual of the periodogram, there is no peaks.
You have 2 minutes. Huh? Oh, sorry. You got your 10 minutes. You have 5 minutes.
Okay. So we also perform the bisector analysis on the PARAS data, and to check whether these signals are coming from activity on the surface of the star or the contamination from the nearby stars. So we checked the correlation between radial velocity and bisector velocity span, and found the correlation coefficient of 0.15, which is not significant. So which shows which also supports that a companion around this star TOI-1789. So to characterize star and planetary system, we did the global modeling with the ExoFast V2 software, and for that we used we did the spectral energy SED modeling with so we did
Can you make it full screen?
View.
Okay. For SED modeling, we used EPAS, 2-mass and WISE data. And here these blue points shows their photometric magnitudes. And these the best fitted model. The models which we used are Kuruksh models, and to determining the age of the star and evolutionary status, we use MESA isochrones and stellar tracks. So here, this black curve shows the stellar track of this TOI-1789, and we found the age of 2.73 gigayear. This is the best fitted model into the data. This first figure I already have shown this, and the second figure is the phase folded test data. And this is the radial velocity radial velocity data points. So on the left hand side, this figure shows the time series radial velocity curve. So here these black points represent the Paris data points, and green one represent the TCS data point, and these red curve shows the best fitted model. So, and on the right hand side, this is a phase folded radial velocity curve. So by this global modeling, we are getting the stellar parameters are like this. So which shows that our star is a late F-type metal rich star with the metallicity of 0.37. And this TOI-1789b has a orbital period of 3.21 days with a radius of 1.44 and mass of 0.70, which shows that its mass is its radius is evolved as compared to its mass, and it has a density of 0.27 gram per centimeter cube, which shows that it is a fairly inflated radius. And it has a semi-major axis of 0.04, which shows that it is a very close into its star. Now, so now in this figure, we shows the statistics of all the transiting hot Jupiters. And this data is taken from TAPKIT database. So here on the x-axis, we shows the distance of the planet from their host star, and on the y-axis, we shows their evolutionary status. And these are color coded according to their metallicity. And this red dot shows our TOI-1789 star, and which has a metallicity of 0.37. So as you can see in this figure, the closing planets are more common around main sequence star, and here are for the evolved star there are very less planets, and till now only 8 planets are discovered, exoplanets are discovered around stars similar to or more evolved than TOI-1789, and they are orbiting closer to their host star within 0.05 AU. And now in this figure, we show the same statistics of exoplanet, and on the x-axis we represent the radius of the planet, and on the y-axis we represent the equilibrium temperature of the planet. So which shows that this temperature and radius of the planet are correlated. So here, as I previously mentioned, that our planet is inflated and it has equilibrium temperature of 1927, which says that we have detected an inflated hot Jupiter, and it has a total incident flux received by its host star is 3.14 into 10 to the power 9, which is quite high, which indicates that inflation in the hot Jupiter are due to the incident flux. Now I am summarizing my talk, and we detected star and planetary system in which star is slightly evolved, metal rich and late F-type star, and our planet is inflated hot Jupiter, and derived mass and radius are at 4 sigma significance, and the detection of similar types of exoplanets will help us to improve our understanding of distribution, formation and migration of hot Jupiter around evolving star. So we acknowledge the support of these people. Thank you.
Thank you, Akanksha. A nice talk. Now let's open for question. All offline participant first, let's say.
Yeah, it's nice talk.
Can you show the second slide where you have shown the radial velocity variation? Yeah. So see, this movement of the star is phase on. Here I see the star is moving in the plane of sky rather than
it's a age on the observer. You can see this one is the observer, so he's looking at this, means age on condition. This is not a phase on condition.
Okay, okay, good. The bottom one is the observer, so for observer it's fine. This is 90 degree. One other thing is for this 45 centimeter telescope, you have the detection of 2.5 millimeter.
Yeah.
So this is very great, very good result actually. Having just 2.5 millimeter detection, so you need a high stability of less than 1 millimeter. Yeah. How you achieved it? So what kind of exposure you have given it?
We give exposure around average of around 20 seconds.
So even in 20-second exposure, so detection of 2.5 millimeter and stability of less than 1 millimeter is really fantastic. Yeah.
Okay. Okay, any other participant, that is offline participant, do you have a question?
Nice talk. Just two quick questions. First is, you said that there are 7 transit confirmed detection by tests, but still tests considered this a candidate, right? Or I mean, my question is very straightforward. Are you the first person to detect this planet or not?
Yeah, we are the first person.
Then why did after 7 detection they considered it as a planetary candidate, and how you?
These are not planetary candidate. These are confirmed or detected exoplanets that I mentioned in the slide. Like these are not candidates. These are confirmed planets.
My point is, tests have 7 transits detected, so they could have said it that this is a planet, right? I mean,
no. Actually, TAS has a split scale of 21 arc second, right?
Okay.
So within 21 arc second, if there is another star planet, another star, then you can not say that this is a planet. Means so you have to confirm it with your ground-based observation or less plate scale, and also it has a 30-minute cadence. So you cannot, like I previously mentioned, that the error bar in the light radius are 27%.
Why it has a 2-minute cadence too?
No, but this target is observed in 30-minute cadence.
Okay. Okay, any online participants?
Yeah, we also did the RV observations.
Okay.
With the transit, you cannot measure the mass. So
okay, just one more. Your parameter set, they look like very nice, and you have very less error bars. So do you use any modeling for that?
No.
I mean, Bayesian modeling.
Till now, we didn't use
modeling. Yeah, that's what I had.
Okay, thank you. So online, then I don't see any raised hand. Okay, if anyone has any questions, can you write into the chat box or? Okay, nobody. I don't see anyone. So I'll come to the next speaker. Thank you, Akanksha, once again. So I'll go to the next speaker, Parul Janagal. She is from IIT Indore. She will be talking on revisiting the sub-pulse drifting phenomena in PSR 1822-2256, drift modes, sparks, and emission heights. Parul, then please share your slides.
Yes, sir. Are you able to see my slides?
Yeah, now I can see. Yeah, please go ahead.
Okay. Wait a second. So hello everyone. I'm Parul Janagal and I'm a PhD student at IIT Indore. I'm going to present a short summary of our group's recent work on the sub-pulse drifting in Pulsar J1822-2256. To begin with, pulsars are formed when a massive star with mass up to 8 solar masses goes supernova. A large chunk of the star's constituents are thrown out, forming a supernova, and at the center, a neutron star is left. These neutron stars are highly magnetized, massive, rotating, compact objects, which emit radiation from their magnetic poles. In certain cases, the radiation coming from the neutron stars poles crosses the observer's line of sight. This is when we see a pulsed emission as shown in this GIF. Can you see my cursor? I guess not. So the study of these pulsars is deemed important as they are tools for understanding some long-standing questions. They have been useful tests for gravity, for identifying the equation of state for superdense matter, for detecting gravitational waves, and many more. The field has also, so this field has also attracted 2 Nobel Prizes within the first 30 years of the discovery. But even after all of that, we still do not understand everything about pulsars. We do not fully understand the mechanism behind such highly energetic and coherent radiation or where it is coming from. What happens inside the neutron star, its structure, and the behavior of matter at such high density and gravity are also the kind of questions that people are looking answers for. Also, the evolutionary cycle of the neutron star and related systems like binaries are some of the open questions. Over the decades, people have tried to use multiple methods to answer these questions. So pulsars are wideband emitters. So people have studied a variety of pulsars and a large class of pulsar phenomena over a wide range of frequencies. We are specifically interested in the first question that is related to the pulsar emission. And we try to understand it by studying the phenomena of subpulse drifting. As I said earlier, when the pulsar beam sweeps through our line of sight, we see a pulse. For some pulsars, when these pulses are stacked together, we see a subpulse drifting feature with longitude. And these slanted features are called drift bands. Oftentimes, for some pulsar, this pattern changes, representing different drift modes. This particular pulsar that we are studying shows multiple kinds of subpulse drifting modes, along with nulling. So the animation on the left-hand side shows the drifting feature forming with each pulse. So you can see these slanted pulses coming with each pulsar rotation. And this is real UGMRT data that we took for this pulsar at 400 megahertz. So with all this interesting phenomena, this pulsar gave us an incredible opportunity to understand the pulsar emission physics. The earlier studies of single pulses were done with smaller arrays or telescopes with less sensitivity. Now, with the current technological advances generating multi-frequency and high sensitivity data, it is worth revisiting these sources. For this project, our data set was taken from the upgraded giant meter wave radio telescope at simultaneous dual frequencies. In this observation, we used the UGMRT in a sub-array mode, where a dozen antennas were configured at band 3 and around the same number at band 4. The observations were taken in the phased array mode at 2 epochs, which were 10 days apart. And we got about 2,900 pulses in our first epoch and about 1,700 pulses in the second epoch. So in our study, we found 4 different kinds of drifting modes that we labeled A, B, C, and D. The boxes and the profiles are color-coded. So red corresponds to mode A, green to mode B, blue to mode C, and black to mode D. I will follow the same convention throughout the presentation. So the pulsar tends to switch between these modes over time. So with each mode switch, the pulsar also changes the average profile along with the drifting pattern. So for modes A and D, the pulsar behaves quite normally, meaning that there are very well-defined drift bands. However, for modes B and C, the pulsar shows intermittent absence or lack of intensity for a couple of pulses, which appears like small nulls. Now, nulling is an interesting phenomenon. In pulsar emission, that we do not yet fully understand. So historically, a pulse is treated as a null if no emission is seen below the detection threshold, which obviously depends on the sensitivity of the telescope. Now, with higher sensitivity and wider bandwidths that are possible, it is also possible to search for weaker emission. And it looks like for at least this pulsar, there is some weak emission during some of the so-called nulls. The pulsar shows regular broadband nulls or real nulls, but while the pulsar is in mode B or C, it shows other null occurrences different from the real nulls. They are different in the sense that the average profile of these pseudo nulls showed low-level pulsed emission at both the observing frequency bands, band 4 and band 3. These kinds of null have only been found in a handful of other pulsar. A possible explanation in this case for these pseudonulls could be that For these pulses, the line of sight is crossing through a minimum of sparks, therefore showing some residual emission. Apart from this, there is a small percentage of the data which we could not categorize in any of the modes, A, B, C, D, or real nulls or pseudo nulls. So in this pulse stack below, the horizontal one, you may notice that the pattern of these drift bands is changing with time. These different kinds of drifting patterns can be quantified using a value called P3, which is the vertical separation, or in this case, horizontal separation between the drift bands at a given phase or longitude. We did this exercise for the whole data for both epochs, and the bar plot on the top shows these P3 values. The different colors correspond to the different drifting patterns of drift modes in this corresponding to the rotated pulse stack below. The values are not a constant number, but they actually form some kind of a distribution. So one of the early models of subpulse drifting suggests the presence of sparks on the polar cap in this shape of a fairground carousel, which rotates around the magnetic axis, giving a drifting feature in the pulse stack. These sparks are basically locations of pair production avalanches near the pulsar surface. The particles produce high energy curvature radiation in the radio part of the spectrum, and that is what we observe. And because of this E cross B drift, these sparks move in the azimuthal direction. Therefore, the geometry of the emission beam would be a carousel of sub-beams circling around a common point in the pulsar sky instead of a static cone of emission. Using that model, we estimated the possible number of sparks for modes A, B, and C with a carousal rotation rate P4, shown in this table below. From our calculations, we found two different solutions of sparks for the carousal rotation rate in the range of 13 to 16 P4. P4 in the range of 13 to 16. So for both of these solutions, the number of sparks only change by 1 when the pulsar switches from one mode to another. Further, we exploited the wide bandwidth to study the frequency dependence of the average profile for this pulsar over different drifting modes. The profiles changed with frequency according to the radius to frequency mapping model, where the high radiation frequency, high energy radiation comes from lower heights and the low energy emission comes from higher altitudes. The left-hand side plots show the average profiles at band 3 and the right-hand side plots show band 4. Mode A remains almost the same, except that the profile gets a little bit sharper at higher frequencies. That is band 4, which is expected from the RFM model. And mode B shows a much drastic variation in the intensity of the components of the profile. Similarly, modes C and D also showed change in average profile over frequency, apart from the profile becoming sharper at the higher frequencies. So to all of these average profiles, we then fitted a double Gaussian function to find the position of the peaks in the profile subcomponents. The yellow region in the plot shows the pulse width at which the intensity drops to 10% of the maximum. So now, because we had a wide bandwidth of 200 megahertz, we could further divide up.
You have 2 minutes.
Yes, sir.
You have 2 minutes.
Yes, sir. Sure. Yeah. Sure, I'll wrap it up soon. So because we have this wide bandwidth of 200 megahertz, we could divide our data into smaller bandwidths without having to compromise the signal to noise ratio. Therefore, we finally had 4 observing frequencies: 350 megahertz, 450 megahertz, 600 megahertz, and 700 megahertz, each with a bandwidth of 100 megahertz. Then we did the same bimodal Gaussian fitting like that I showed in the last slide for all the 4 modes and noticed some kind of evolution for each component with frequency. In these plots, the orange points denote the leading peak in the modal average profile, and the blue points refer to the trailing peaks. Now you can notice an evolution towards the right-hand side with frequency for all the components, implying that the line of sight is actually cutting through conal sparks. We do not see such an evolution if the line of sight was cutting through the core sparks. And also note that the average profile of the pulsar had its peak coinciding at 0 longitude, but the individual modes show this kind of evolutionary behavior. Using all of this information, we calculated the emission heights for each mode. Here, alpha and beta are the angles that define the pulsar geometry. W10 is the pulse width, and gamma is the angular width of the emission beam. Interestingly, we found an inverse relation between the emission heights and the P3 value for each mode. Therefore, mode B, which had the lowest P3 value of about 5, was emitted from the highest heights, whereas mode A with the largest P3 value had its emission coming from lower heights. From some of our sparks calculation, a correlation between P3 values and the number of sparks can also be inferred. And if such a correlation is indeed true, this will imply that the number of sparks in a mode are directly related to the emission height for at least 94% of the emission for this pulsar. All of these results and the details behind them are mentioned in the paper, which is now published in MNRAS. I'll leave you with the summary slide. Thank you for listening.
Thank you. Thank you, Parul, for doing it well in time. Then I will have questions from online participants. Oh, sorry, offline participants first.
Offline participants.
Yeah.
Sorry, I could not hear that.
Okay, I'll take the online. Just Yashwant, then can you unmute yourself and ask your question? Host, can you please unmute Yashwant? And...
Yes.
Yeah, please.
Yeah, okay, good. Thanks. That was a very nice talk, Parul. I had a couple of questions, but I'll ask only one right now.
Yeah,
so
please.
this last part where you estimate the emission heights, if I'm not mistaken, this assumes that you are using a certain particular field line location. I think that's S in your equation, if I'm not mistaken. Yes, so what did you, I mean, if you change that, then these numbers would change, right?
Yes, they would change, yes.
So you're assuming that S to be at the edge of the open field line region or somewhere else? Or?
Yes. No, I'm expecting that to be the edge of the open field line region. And the reason was because from this previous evolution, we could see that there is a conal cutoff, a conal line of sight cutting. So it seemed like a natural thing to do, to keep S equals to 1 in that case.
Okay, yeah, that's fair enough. But one way to check that is if you have a much higher frequency profiles for this pulsar, whether you see additional conal components emerging, in which case it'll tell you that this is probably not the last open field line that you're looking at, but that's something you probably should be able to cross-check.
Okay. Yes,
yeah, okay, thanks.
Thank you. And now, Valchan, please go ahead.
Yeah, Parul, I think a very interesting talk. It's a very beautiful pulsar to sort of study various things. Remaining on this slide, so there is also the asymmetry in the profile with the leading and the trailing components. So my question to you is that the calculations which you have shown here in terms of the emission heights, do they correspond to the asymmetry in the profile? That is, are these consistent with the expected asymmetry in the profile?
So the asymmetry is, I think, ingrained in this value W10, which is the width. So it is taken care of kind of when we calculate these emission heights. If that answers. So like here, there's the profile is indeed asymmetric, but we use the W10, which is the width at when the profile intensity drops to 10%. And I guess that is where you take this asymmetry into account when calculating the emission heights.
Okay. Okay. Is it answers well? Okay, fine. Now next by Yogesh. Can you unmute yourself? And
yeah, thanks, Parul. Very nicely presented work.
Thank you, sir.
You mentioned that the number of sparks seems to be correlated with the emission heights. So how do you interpret it? The number of sparks are somehow decided by the plasma processes at the polar cap, but the emission is much farther away from the star.
Yes, but the sparks that are leading to this emission, they are getting formed at the around the surface, right? So this was just a kind of correlation, small correlation that we found that our number of sparks are just changing by 1 unit. And if for modes A, B, and C, and there is a straight correlation between those number of sparks and P3. And then there is a correlation between P3 and the emission heights. So it seems like there could be a correlation between the number of sparks and the heights. Now, I cannot exactly comment on what phenomena could be giving rise to this kind of dependence, but I guess that is for the later studies to explore.
Okay, thanks. But one possibility could be that when the number of sparks are varying, the radius of the circle on which these sparks are generated, that is also varying, and that might give rise to this kind of correlation.
Okay.
Yeah, thanks.
That could be possible, yes.
Yeah, thank you.
That could explain the widening of the profile at different modes. Because the profile width also changes at different modes.
Yeah. Thank you, Parul, for your nice talk. I'll move ahead with another talk that is from the Pratik Tarafdar. He's from Indian Institute of Mathematical Sciences. We'll be talking on the Indian Pulsar timing array 3.5-year data release. Can you please run the Pratik's talk, LOC?
Yes, sir. We are doing that.
Okay.
Yeah, we are doing that.
You have to stop it.
So it's visible, right?
Thanks for giving me the opportunity to deliver this talk.
Yeah, it's visible now. Yeah. Yeah, please run.
Thanks for giving me the opportunity to deliver this talk. I'm Pratik, and I'm working as a postdoc at the Institute of Mathematical Sciences, Chennai. I'm speaking on behalf of the Indian Pulsar Timing Array, which is a collaboration of a large number of institutes both in India and abroad. Especially, we have colleagues from Japan and Europe, and together with the International Pulsar Timing Array Consortium, we are searching for nanohertz gravitational waves in the pulsar timing data. This is going to be a brief update on our first data release and some related scientific projects on board. Pulsar timing arrays, or PTAs, are expected to detect gravitational waves with frequencies in the nanohertz range, which is orders of magnitude lower than those from events being detected by LIGO, or that are expected to be detected by space-based interferometers like NISA. So what is pulsar timing? Pulsar timing is a technique to measure the pulse arrival times from the pulsars. Ideally, the pulses should be periodic, but precise measurements actually reveal discrepancies due to propagation delays. Among the many sources of these delays, the ones which we seek for are the nanohertz gravitational waves. But detection of such delays requires submicrosecond time positions, which is available only for extremely stable and precise pulsars with periodicity in the orders of milliseconds. These delays begin right after the emission. Since most incident pulsars are binaries, the signal encounters lag near the source itself. Similar delays occur during its passage through the solar system. The revolution of the Earth around the Sun and Earth's own rotation requires additional clock corrections. However, the most difficult delays to model are due to vast oceans of cold ionized plasma that we observe around the Earth. Provided we know all these delays, their subtraction from the pulsar arrival times of an array of pulsars, a carefully selected combination of certain millisecond pulsars, should leave us with the nanohertz gravitational wave signatures as correlated noise in the combined signal. The PT astronomers are presently after this elusive correlation, which is also known as the Hellings and Downs correlation, named after Professor Ronald Hellings and G.S. Downs, and we sadly lost Professor Helings on the 1st of January this year. We now have a global consortium called the International Pulsar Timing Array, which brings PTA organizations across the world under one umbrella. The IPTA presently consists of nanograph from the USA, the European Pulsar Timing Array, the Mars Pulsar Timing Array from Australia, and the Indian Pulsar Timing Array from India and Japan. Countries like China and South Africa are also expected to join soon. That brings up the IPTA. Since the upgraded GMRT is highly sensitive at low frequencies, the IPTA data would be ideal to study the interstellar medium delay effects that are most prominent at lower frequency regions. The IPTA experiment was conceived back in 2015, and presently we are observing around 14 pulsars with approximately 10 to 14 days of cadence. All of the IPTA data is recorded using the upgraded GMRT, which consists of 30 antennae distributed in a central square and its Y-shaped arms. The upgraded receiver makes it possible to conduct simultaneous observations across 4 separate frequency bands with upgraded servo systems, front ends, and digital backends. Coming to the data release, it has a baseline of slightly more than 3.5 years. We have been observing a total of 14 millisecond pulsars, out of which around 7 have been consistently observed over the entire time span, with approximately 10 to 14 days of cadence. We have 200 meters of bandwidth in each of band 3 and 5, and the final products that are expected out of these data release would be the pulsar arrival times, or TOIs as we call them, and the time series of dispersion measures, which is a measure of the interstellar medium. And the estimations are going to be from both traditional as well as certain novel state-of-the-art techniques. This is the table of our observational setup across the cycles. We also have simultaneously recorded band 4 data, but only for the earliest cycles, as later we decided to increase our resolution with the lower sampling times, which would mean storage constraints, and hence we could afford to record only band 3 and band 5 data during the later cycles. The reduction of raw data to analyzable data happens over a pipeline named PINTA, and that was developed by Abhinanyu Shushoban and et al. We are also developing a legacy pipeline called LPINTA to reduce all the older GMRT and repeaters of data back to 2015. If you are interested in knowing more about these pipelines, please have a look at the posters presented by our colleagues Adarsh Vatula and Arul Pandey. The traditional narrowband timing involves cross-correlation with templates having full frequency resolution in each band. Misalignments due to dispersion across the bands is mitigated by fitting all the channels in both band templates for an average TM. The alignment ensures that we do not require fitting for any fictitious frequency-dependent delay parameters while obtaining full timing solution, which otherwise is needed by some of the other PTAs. This is basically an advantage of our low frequency data, which allows us to have a closer look at the ISM effects and to obtain better timing residual fits. Here's a preliminary look at the TOIs generated for all 14 pulsars. To state this simply, these are the leftover or the residual delays in pulsar arrival times after fitting for and subtracting other known delays. In our case, these include residuals from frequencies much lower than those usually from the remaining PTAs, with ISM-related delays measured from our own data and subtracted from the TOIs. While dealing with the interstellar medium, we still get sub-microsecond order time precision in many pulsars, which is encouraging. This data has been very recently shared with the European PTA, who are really excited to work on it, and together we are trying to combine their data from various high frequency receivers with our low frequency data for a global picture of this phenomenon. In addition to the traditional method, we are also going to deliver TOIs and dispersion measures generated using a relatively recent technique named as wideband technique, which makes use of principal component decomposition of two-dimensional templates and their subsequent reconstruction with high signal-to-noise eigenprofiles that are parameterized with frequency. In simple terms, this technique can possibly revolutionize the way of dealing with frequency-dependent profiling illusions. We are still a few days away from the first run of wideband results for all our pulsars, but the existing ones already show far more precise residuals. We have been applying this technique only on band tree data so far, but extension to band tree and 509 is on the cards. If you are interested to learn more about this wideband technique, please feel free to pester our colleague Milky Way in the poster section. The ISM effects characterized by dispersion edges have always been notoriously troubling the PTA community. Delays due to the interstellar unbiased medium primarily manifest in the data, either in the form of irregular dispersion or turbulent effects causing multi-path propagation of the signals, such as scattering and scintillations. And this is where the PTA data is most valuable. The dispersion measure estimates from simultaneously recorded multi-band data, including lower frequencies, have significantly high precision. In some cases, the achieved precision is indeed unprecedented. And the application of both traditional as well as wideband techniques, we believe, is only going to make things better. The high precision measurements help us to have a very close look at the epoch by epoch ISM variations along with given pulsars line of sight. For instance, what you're looking at are the dispersion measured time series obtained from narrowband technique for all 14 PTA pulsars over their available baselines. Estimations are done using DMCAL, a script written by Krishna Kumar et al., which is an elegant combination of traditional pulsar data analysis and timing softwares, along with intelligent regression-based analysis. And the time series obtained would enable us to do modeling of DM noise in real DM data, which is quite fantastic. Also, if you look at the data for some pulsars with the most notorious ISM effects, indicates the necessity of considering stuff that are usually ignored by the other PTAs. These effects include variable scattering. In fact, presently there is a PTA project to simulate scattering with variable index and look for the resulting gain estimation offsets. It is very interesting work led by Jeewan, who is a student of IIT Roorkee, and I would really encourage you all to go and have a look at this poster. As mentioned earlier, we are also going to have the DM time series from wideband technique for all the pulsars. It is work in progress, being led by Yogesh Maan and Prerna. Details can be found in Nikita's poster of the wideband estimations. Let me end by mentioning another interesting work. Between April 16th and April 17th last year, radio telescopes across the world observed a sudden change in the profile of a pulsar named J1813-0747. It is among the highest ranked PTA pulsars. So a change in its fingerprint naturally raised a lot of eyebrows in the PTA community. Nanograph was the first to report the change at high frequencies using Chime, while PTA was the first to observe the change at lower frequencies. We also established the effects it would have on the time residuals in both band 3 and band 5. The results are significant, and a detailed analysis of this event is underway. The true reason behind this event can only be unearthed upon an exhaustive investigation from a low frequency perspective. Details of the reported results are already presented by our colleague Neil Gordon in the poster section. To summarize, we have a number of projects on board at present. We are already working with the EPTA data combination group towards IPTA data release 3, various scattering simulations as I just mentioned, frequency dependence of decorrelation bandwidths, 1713 profile change, wideband analysis of all EPTA pulsars, investigation of mixed pulsars with suspected mode changing behaviors, characterization of solar events from pulsar timing data. Then we have proposed projects on single pulsar noise analysis, single pulsar noise and timing analysis, and gravitational wave analysis, and of course, the science behind supermassive black hole binaries and other background sources. Preliminary signs of Earth's gravitational wave detection are already reported in NPTEDR2. The hope is with the inclusion of low frequency NPTED data could help us hear a final word on the detection in the upcoming NPTEDR2. Please stay tuned and visit our website for the latest updates. The website got launched just 2 months back, and I just mentioned that the website has been designed by a very young member of the Guard mission. His name is Yogesh Maan, and he also happens to be an undergrad at IIT. Speaking of which, I feel tempted to flash the faces of this vibrant team. Each one in the group, be it a faculty member or postdoc or a PhD student or an undergrad, has a tremendous amount of energy and enthusiasm. I thank this wonderful team, and I thank you all for giving me this opportunity to speak. I'd be happy to take questions. Thank you.
Thank you, Pratik. So any questions from offline participants?
Hello. There seems to be no question from the offline.
Okay, fine. Now online participants, any questions? Though the audio is a bit poor, so we are hardly to hear some.
Yeah, actually, sorry. I think the audio that was played on Zoom was not in line. So the online participants, including me, we were hearing a lot of reverb actually.
Okay. So if anybody has a question, then they can write in the Slack channel as well as in the chat box. So otherwise, I'll go for the next talk. So next talk is by Yogesh Maan. So he is from NCRE and we'll be talking on 800 days of magnetars XTE 1810-197 insights from radio emission. Yogesh, please go ahead. So I'll ping you 3 minutes before the talk, before your discussion time.
Yeah, thanks. Good afternoon, everyone. Thanks to previous speakers. There was a good flavor on pulsars and how they emit in radio, and yeah, and the pulsars form a major part of the neutron star population that is observable or that we know of. So from there, I am going to take you to a much smaller fraction of this neutron star population, but this small fraction exhibit quite exotic behavior. So these are called magnetars. So what are magnetars? Magnetars are isolated neutron stars, and the word isolated is quite important here. Compared to the normal neutron star population or the pulsar population, the progenitors of magnetars are likely to be on the heavier side. And most of the magnetars are detected in high energies, and some of those also are detected as bright X-ray pulsars, even in their quiescence mode. And all of these magnetars are quite active in high energies, and by high energy I mean again soft X-rays, hard X-rays, and soft gamma rays. They exhibit a number of events like outburst, flares, durations of which can vary from sub-millisecond to minutes. And then a few of these objects also have exhibited giant flares. These objects, magnetars, exhibit the highest magnetic fields that we observe in the universe, of the order of 10 to the power 14 to 10 to the power 15 Gauss. And these high magnetic fields are basically the reservoirs of energy which has been attributed to their emission in the form of outbursts and flares, etc. They are relatively slow rotators with periods in the range of several seconds, and some of those, and only sometimes, exhibit transient radio emission. And that's the radio emission I'm going to talk about in the rest of the talk. So we know about 32 magnetars so far, quite small number, and only 5 out of these 32 magnetars have been found to exhibit radio emission, and that too transient. Most of the time, the radio emission has been seen to be associated with an X-ray outburst, The radio flux decays with X-ray flux, but the onset of the radio emission is perhaps delayed. It's still not clear. And we see remarkable variability in the radio emission. And at least till recently, the radio spectrum was considered to be flat or inverted, as opposed to steep radio spectra we know from pulsars. So there are a lot of open questions when we come to magnetar radio emission, and not much is known about it. So for example, what decides that only some of these objects exhibit radio emission and that too transient and not others? There are some theoretical models, and I'm not going to go in details of those. What decides the onset of the radio emission, or why the radio emission itself disappears after some time, and the time scale for that, for which the radio emission remains visible? The time scale itself can vary from days to months to even several years. What causes the temporal and spectral variability, as opposed to pulsars, for which their average profiles are considered as like their fingerprints, in the sense that you observe the average profile of a pulsar today and after 10 years and it will be same. But for magnetars, it can change within a day or within just about an hour or so. And one example is shown here on the right side. What kind of links there are with the normal pulsar population? So for example, are there evolutionary links between magnetars and normal pulsars and other kind of neutron stars? And what kind of links in terms of the emission physics which underlie in these objects and give rise to radio emission, but only in the form of transient emission? And perhaps it's probably more well known that there are a number of theoretical models which advocate that magnetars are the originators of fast radio burst, the small millisecond duration radio burst of extragalactic origin. So with that sort of introduction, the rest of this talk, I will focus only on one object. And with these kind of open question, we know that there is enough motivation that given the sparsity of detection of radio emission from magnetars, and also that the fact that we know only a handful of these objects, it is important to characterize the radio emission from these objects whenever it becomes visible. And with that motivation, I'm going to present a characterization of one of these objects, which is named as XTE J1810-197. In fact, this was the first magnetar from which radio emission was detected, and it came out as a surprise because given their very high magnetic fields, excuse me, given their very high magnetic fields, earlier people had expected that these objects will not be visible in radio. But this object first showed an X-ray outburst in late 2002. After about a year, this object was observed in radio, and that was in imaging mode, and surprisingly there was a radio source at the position of this source. After another 2 years or so, despite not too much expectations, people did conduct time domain observation of this this object, and surprisingly found pulsed radio emission. And this kind of established the link between magnetars and radio pulsars, and also ruled out the alternative theories which assumed that there could be very low mass companions to these magnetars, and these may not be isolated. So the radio emission from this object eventually quenched in sometime around 2008. And after about 10 years of quiescence, regular radio monitoring revealed that the radio emission has again restarted from this source in 2018. Although the X-ray emissions were not being, could not look at the source because of the proximity to the sun, but eventually they did deduce that there was an X-ray outburst just before or around the same radio outburst. We detected the source with GMRT in band 3 and band 4, so range in the frequency range is from 300 megahertz to 750 megahertz, very close to its outburst. And with that success, we embarked upon a observing campaign, and that is still going on. And what I'm going to present a few peculiar properties or some characterization which we have uncovered in first 2.5 years of this monitoring campaign. So this is just a summary of our observation, which shows the whenever we observe this source and the frequency ranges in which this source was observed. So the first property is the radio flux density, and you see here 3 colored points. The color convention is red color is for the lower frequency range, 300 to 500 megahertz. The green color is for the medium frequency range, which is 550 to 750 megahertz, and the blue color is for the slightly higher frequency range, that is in L band. You see there are a lot of flux density variations, and you see that the lowest frequency is just about a millisecond, millijansky, or a fraction of that, but the highest flux density reaches as much as 60-70 millijansky. So factor of 50 easily, and this cannot be explained by any interstellar medium effects. So these kind of wide variations are intrinsic to the source. If you look at the X-ray flux density, and so X-ray flux, which is in purple colored dots here, we see that there is a monotonous decay in the X-ray flux, and there is hardly any simultaneous or as wide variations as in the radio. So although the radio emission might have been onset by an X-ray outburst, but once it is onset, the radio emission is very dynamic. If you look at the spectrum of the source from one epoch to other epoch, and you see that there are again wide variations in that, to an extent that sometimes it's inverted and sometimes it's quite steep. As a function of epoch, again you see that the source started near closer to the outburst in a spectral state which was kind of inverted with positive spectral indices. But as we go farther and farther away from the outburst, the spectrum has become steeper. There is another thing to note here. There are again 3 colored points, and that again indicate that red colored points, the spectral indices estimated from the lower frequency range, the green points from the mid frequency range, and the blue colored points from the higher frequency range. And you see that the red colored points, so the lower frequency estimates, and the blue color, the higher frequency estimates, sort of encompass the mid frequency range estimates, and eventually they tend to merge with each other.
You have 3 minutes.
Yeah, okay, thanks. So this might indicate that there's a spectral turnover somewhere in this frequency range, and to estimate that, what we did was we tried to construct broadband spectra of the source using our own measurements as well as several published literature estimates. And when we do that and see as a function of epoch again, the chronological order from left to right and top to bottom, that there's a turnover in the spectrum, and not only a turnover, the turnover itself varies with epoch. And you see that as a function of epoch, the turnover rapidly moves towards lower frequencies. So this is the turnover itself has been seen a few other magnetars, but the shift in the turnover, and that too with that kind of gradual shift, is the first time we are seeing in any magnetar. So how to explain the turnover as well as its shift? One possibility is that there was a thermal absorption in the medium somewhere. We could explain that, but there are 2 major issues. One is along the line of sight, we do not see any presence of such thermal medium which could give rise to this turnover and the shift. And because we see a shift, this thermal medium has to be dynamic, and there is no known associated supernova remnant or the wind nebula with this source. So we believe that the turnover as well as its evolution is likely intrinsic to the emission mechanism of this source. Okay, I will skip this third property, but we'll go to the fourth one. The magnetar also emits very bright pulses quite frequently. And if you look at the individual spectral properties of these bright pulses, so for example, a sample of those are shown here, you see that their spectrum have this patchy emission. So for example, the first plot here at the top corner, the emission is constrained within about 50 megahertz or so. the next one is, again, the emission is patchy in a few tens of megahertz or so. One would think that this patchy emission might be just, again, effect of the propagation caused by interstellar scintillation. But we can also measure, if it is caused by interstellar scintillation, the effect in terms of the scatter broadening. And if we do that, we can estimate the scatter broadening, and from there we can deduce what kind of bandwidth would have been caused by the interstellar scintillation. And that turns out to be only about 1 kilowatt or so. So that is several orders of magnitude smaller than what we see here. So again, this kind of patchy emission is probably and most likely intrinsic to the source. If you go to the literature and see what kind of other sources have shown this kind of patchy emission, there are only two types. One is giant pulses from the crab pulsar, but at very, very high frequencies, several tens of gigahertz. And the other is the emission from several repeating fast radio bursts. The repeating fast radio burst, although those also show patchy emission, they also show much more detailed structures. So although there is some sort of analogy, there is not really one-to-one correspondence. So in this context, if we also compare the properties of these bright pulses with giant pulses as well as FRBs, there are stark differences as well. So we can't really conclude at this point whether there is a really one-to-one correspondence between these bright pulses and the other kind of known pulses which have shown similar spectral properties. So with that, I would summarize that we have uncovered a few peculiar behaviors in the magnetar 1810-197, and two in particular, which I still want to emphasize here, is the gradual steepening of the spectrum caused by a turnover which evolves with the frequency, evolves with time. And that's the first time ever someone has seen it in a system which is which we hard to associate with any thermal absorption kind of explanation. The other one is the bright single pulses with very intriguing spectral properties. And both of these properties are likely to be intrinsic to the emission mechanism rather than caused by propagation effects. But the future more detailed characterization might throw more hints on that direction. And probably due to the scarcity of the detection of the radio emission from these magnetars, there is hardly much progress on the theoretical side, and it's high time that happens. And there are many open questions which still need to be addressed. With that, yeah, thank you very much for your attention.
Thank you, Yogesh, for nice talk. There is a question from Shushan. In the flux evolution figure, the radio and X-ray fluxes appear to be anti-correlated. X-ray falls and radio rises. Do you understand this?
So not only that, so in the beginning phase, there is a correlation where the radio also fades and the X-ray also fades. But then the radio shows these episodes of rebrightening, one here and there. It might appear that like there is anti-correlation and one here, but it's not always one-way correlation or anti-correlation. But if there is any physical relation between these two, that's not very clear at the moment. And it seems like there is not much except the radio emission is onset by an X-ray outburst.
I can take up one or two questions quickly. Offline participants?
No offline question.
No. Online? No. Nobody's raised hands. Okay, thank you, Yogesh, again.
Yeah, thank you.
I'll move to next talk. Next talk by Akshat. He's from IIT Mumbai. He'll be talking error analysis in high energy pulsar period estimations method. Akshat, please go ahead.
Yes, is my voice audible and mouse visible?
Yes, everything is okay.
Excellent.
Please go ahead.
Thank you. I thank ASI team for allowing me to have this presentation. I'm giving this talk on behalf of undergraduate student Ishan Jain and Professor Bhalerao. So it's about understanding the error when we try to estimate period from high energy pulsars, X-ray or gamma. Firstly, I would like to give some background. When we consider high energy pulsars, the mathematical rigorousness in the literature is often missing regarding the methods within which people calculate the error. Since we are talking about high energy pulsars in X-ray and gamma regime, they are very, very photon limited. So we receive very less number of photons per second with our instruments. And therefore, these are what we call Poisson limited data. So their statistical distribution is based on the Poisson stats. So we tried to run some Monte Carlo simulations. We simulated some pulsar-like signal and then recovered them and tried to understand the distribution of the parameters extracted, tried to assign an error value to it, and then try to understand if there is a power law-like behavior for those error. And that's what the talk is about. So let's start from the basic, let's say a very simplified pulsar signal, one harmonic sinusoidal A plus B sin omega t. So it's a non-stationary Poisson signal. There are ways to simulate how the data should look like. We use a pipeline in Python. On right hand side, you will see if the signal shape is 50 plus 40 sin omega t, then how the bin data looks like. But what we actually get are the individual arrival of photons. So we know, okay, one photon arrived at 8 a.m., next photon arrived at 8 a.m., 1 second, and so on and so forth. And using this, we have to identify what's the periodicity and other parameters. So we have arrival of time of each photon. What we do, we subtract the time of first photon, and now in order to get the period, we first have to guess. We say, okay, let's assume that the period is 1 second, calculate the phase of each photon. Once we have this phase, then we calculate the measure of periodicity. The most currently commonly used method is this Zn square method. It was first introduced in 1983. There are other methods in literature, epoch folding and edge test. They are family of within the family of each other. So we will focus on Zn square method. So we have phases of each photon. We use this formula to plug it in. For simplicity, we can use n equal to 1. We only use one harmonic, and our signal is anyways sinusoidal. So what we get this Zn square plot. It peaks around the frequency or the angular frequency which we are looking for, and whichever is the maximum value, that's your period or the angular frequency of the signal. Liahi has shown that this shape is supposed to look like a sinc square, and we will use this to actually extract this. So for one simulation, we have got one value of period. We do this multiple times, we get the statistics of period of the derived parameter, right? Compared to, so we have presented this last year in the poster presentation, the same talk. So there is an update over this. We have now derived a proper mathematical function for the expectation value of this Zn square plot, and it looks something like this. We will study this in detail in further slides. So now you have your period. So what you can do, you can understand the phases better, and now you can phase fold your data, and if you bin them, you will get the original shape back, and by curve fitting you can get approximately the same values which you injected this. Once you do this several number of times, you have statistics of all the derived data. Point to note, and some of you might have already noted, that for this you need to a priori know the function. We often won't know. So yeah, this is just for the study purpose, and we will focus only on the period because rest of the parameters often we won't have access to. So if we, let's say, do this simulation thousands of times, you will get this quotient distribution centered around the actual frequency, in this case angular frequency, and you can use this X as an actual measure. So there are two kinds of units we defined. One is the median of absolute deviation. That means you subtract the actual angular frequency from all the recovered parameter, take the absolute value of that, and whatever is the median, that is your measure of error. If you define it this way, that will have a 50% confidence interval. Median is more robust to outlier, or you can simply take 3 sigma clipped standard deviation. This will have 68% confidence, more or less. Yeah, and this is what we call the error. Now understand how this is the error. You have used the same input parameter to simulate a pulsar-like signal. Let's say 1,000 times. You recovered the parameter, and in those 1,000 realization, this was the distribution. So you will say, if I have some value of period, I don't know what the true value of the signal could be, because this is how the distribution works. Yes, now once armed with this way of defining error, let's see how it behaves when we fine tune our input parameters A, B, omega t. Our signal looks like A plus B sin omega t just for refresher, and we observe it for a observation time t. So if we let's say vary only parameter A and keep rest of them constant, so we expect that in a log-log plot you will see some power law-like behavior. We see this more or less straight line, and we get an exponent for one set of B omega naught t when we have. When you also do this for multiple parameter set, you get different power laws. And now in previous year poster presentation, we included the contribution from these outliers. Much later, we realized that these outliers are from very low SNR and low observation cycles. As you see, all of them are from purple color regime, and that means a very low observation time and apparently signal to noise ratio. When done in this fashion, you get approximately the power law numerically computed A to the powers and so. If you try to approximate it to or round off to the nearest whole number ratio, this is what we get. But right now we don't know if this is dependent on the parameter set we chose. We chose period varying from 1 to 5 seconds roughly. This A and B is number of photons per second, roughly ranging from 75 to 750, and B from 25 to 250. Yes, this is in some sense much higher compared to what real data is corresponding to, but it's for the analysis and study purpose. So right now we have this value, and we need to scrutinize it further. Now, again, coming to what the error means. If you see, if you do this thousands of realization, you will notice that this peak itself shifts a lot, and this is due to the Poisson nature of the data. However, a lot of literature and some of the period estimation data available in public domain includes the error corresponding to the, let's say, curve fitting routine. You try to curve fit sinc square or Gaussian into this, and whatever error the curve fitting routine returns, which is often the covariance metric, the square root of diagonals of covariance metrics or other output of this curve fitting routine, they are solely a function of the variation in your data compared to the model and number of your data points. So if you compare what the curve fitting routine actually returns and compare it to what the actual deviation of this peak is, you will see that the ratio is a couple of order of magnitudes higher, often going to as high as 90 times compared to what actual data is. So curve fitting routine underestimates the error by a couple of order of magnitude. So in the literature, you see similar formula which belong to the family of curve fitting routine. You have Bloomfield and Kovacs and many other routines available. I will not go into the details what each term means, but basically these all belong to a similar family of curve fitting error. And if no context is available and that's the only single data is accessible to you.
3 minutes.
Yes. and only a single data is accessible to you, then that's the only error you should report. But since we have studied the Poisson behavior, we know that the period should be much higher. The other half of the spectrum is the overestimation, in which they measure the width of the period. Again, we will see that this is much on the higher side. So we have the, just to recap, we started with sinusoid. We derived how the Z square plot should look like, and empirically we came up with this quantity. We try to investigate mathematically. If we see the Z square term, we can Taylor expand it and investigate on the second derivative. A much lengthy derivation later, we come up to the realization that the variance of the recovered omega correspond to this. And if you notice, it's exactly the inverse of the second term. Hence, we get this value, which is, if you notice, if you replace it with square root of 25, which is 5, which is exactly the same what we get. So that was not a coincidence, although our assumption during the derivation was that the number of cycles are large enough, observation time is large enough. But as some of you have rightly noted, it means you need to know value of A and B a priori. So we eliminated that in first place as well, and replace it with some constant A and some with W, and doing the similar derivation, we get a pulsar independent, a pulse profile independent method. And we can see now the W doesn't make sense because square root of A is a very dominant term over here. You can do the similar derivation for a generic profile term. We have purposefully made it not used because of other reasons. And then we try to check if whatever we have derived makes sense numerically. So for higher number of cycles when you observe, what is measured versus what the formula predicts, it comes close to 1 for large enough observation cycle. Now the next step obviously is include time gaps, because real data has gaps due to South Antarctic anomaly and other reasons, and also we have to include other shapes. So I will quickly just summarize what the plot says. Within the factor of 2, if you include higher harmonics, if you include time gaps, this formula is still consistent, although some more terms you need to use for your modeling, but still within a factor of 2 compared to order of magnitude, within a factor of 2, you get reasonable data. And the simulation done this time was from 50 milliseconds to 5 seconds, and a lot shorter and lot larger time interval. And obviously this is very computationally expensive. Some of the tests are still running, but we are confident that within a factor of 2, we can now predict the error much better. Obviously, and I will summarize my work from here. The last step is to actually look at the real data. We use associated data for this. Let's say if you look at the crab, crab is not a single harmonic data, it has multiple harmonics. If we just use first harmonic, it nicely fits with our expectation. Rest of the data doesn't, but still, despite of that, we stick to the most simplified way so that other future researchers can also use it, and it's easier to study as well. The outcome of that study was we used CRAB from CZTI data and LaxPC, and another Pulsar 41-second. CRAB has 33 millisecond data. We used different time interval, different harmonics, different number of simulations. The output is CRAB was, because it was much brighter, gave a much healthier value of what formula predicted and what Monte Carlo simulation did. Because this was, the next Pulsar was pretty long. So even for 62 kilosecond, we only had 1500 cycles, which is 2 less, but we still were within a factor of 2, around a factor of 2, even though our number of simulations were also less. And yeah, so in conclusion, we have done Monte Carlo simulation to identify what error should be. We have an empirical formulation. Not only that, we have mathematical derivation that it makes sense. It's consistent with time gap, pulse profiling, even real data. The manuscript is in preparation. And lastly, I will end with what's the importance of getting a better data in itself. If you have better confidence, then you have better models. With better confidence, you have appropriate search regions. If you have a GW search, so if you give underestimation, you will not search it in the appropriate region. If you have overestimation, you will overuse your resources. And period have coupling with spin downs and the remnants. That's all from my side. Thank you for paying attention. Anyone looking for a healthy postdoc in data analysis?
Thank you, Akshat. Any questions?
We have one question offline.
Yeah, please go ahead.
Nice talk, Akshat. So I was wondering, have you tested with long-Scalwell periodograms as well? And what is the differences and the errors with that? And I have a second question regarding, can you go back to the slide where you showed some exponents? What was that? I didn't understand what that was about.
Okay, I think I missed your first question, so I will answer your second question first. So we have error from, we have done multiple realization. We now know what distribution of recovered period looks like. So we now know the error for one set of input parameters. If you do this for multiple input parameters, you can plot some of them on log, where only one parameter varies, others are kept constant, and you will get exponent. If you do this, so for one set of B, omega naught and T, you will have one exponent. You take some other B omega naught T, ideally you should have the same, but because of statistical reasons, they have some randomness to it. If you remove the outlier, which are the low SNR and low observed signals, you get more consistent exponent. So you can then report this quantity here, a to the power 0.49 with the much higher accuracy. If you don't do this outlier removal, then your error term on this exponent is quite high. And yeah.
Yeah, it's still a bit unclear, so I'll catch you on the Slack. First question was regarding long-Scalwell periodograms.
Sorry, what?
Long-Scalwell, LOMB-SCARLG.
No, I'm not aware of this part. Maybe we can talk on Slack better, but I will, if I understand this properly, it's a guess. So if you have more non-statistical noises or your spin down terms, so we have tried analyzing those kind of data as well. But depending on how you calculate, your error terms can vastly differ. I think Slack will be a better place to discuss more.
Okay. Any other questions from online participant? I don't see any raised hand. Offline?
No.
No. So I thank all the speakers. Thank you, Pratik, first. Akshat first. Then I thank all the speakers of the sessions, participants online, both online and offline, for their attention. Thank you very much. So we'll end the session with this.